Hi everyone, my name is Hemant Zunkara. This is my video assignment for the process engineering thermodynamics. Today my topic is the first law of thermodynamics as it applies to cyclic processes. Today we'll start with a quick review of the first law and the crucial difference between state and path functions. Then we'll define a cyclic process and derive its key equations. The main focus will be on two numerical problems, one using a PV diagram and another using a data table. Finally, we'll summarize all these concepts and understand how cyclic systems work using the first law of thermodynamics. First of all, what is the first law of thermodynamics? The first law of thermodynamics states that energy can neither be created nor can it be destroyed, but it can be transformed from one state to another. So, when we decide one or the other state, as represented in the figures on you see on the screen, you can see two states represented on the screen and two paths which you can take to change state from to state 2 or state 2 to state 1. The key concept here is that an internal energy U is a state function. This is like altitude, for example. If you start at the base of a hill and at the top and end at the top of the hill, state 1 and state 2, your change in altitude is the same regardless of whether you took the steeper path up or the less steep path up. However, when we look at the first law of thermodynamics, the change in internal energy is defined as the difference between the net heat added to the system and net work done by the system. These functions are like the effort you put into reaching the top of the hill. So they are different for each path. So the path does matter for work done and heat added, and it does not matter for the change in internal energy. So, what is a cyclic process? A cyclic process is any process that returns to its initial state. So, two assumptions that we're going to make here is since the start state is equal to end stage, the change in internal energy of the cyclic process is taken to be zero. This can be visualized in the figure given on the screen. So, when we derive this equation, when we start with the first law, when the change in internal energy on the Q of the heat added in the cycle and the work done on the system, when we substitute that the internal energy is zero, we get that the Q net is equal to work net. The net heat should be equal to the net work that you get out basically. So when we move on to work on a PV diagram, we can see that when we integrate the pressure and the work done, which is the area under the PV curve, so the net work is equal to the area of expansion minus the area of compression of the process, where the net work is equal to the area enclosed by the curve. So you can see two figures represented on the screen, bottom left of the screen, where you can see work in area of expansion on the left, and then on the right you can see area of compression. When we take the negative of these two, you can see the yellow area enclosed by the loop on the topmost figure on the left. Moving on to some numericals, we can see that when an ideal gas undergoes this cycle here, A, B, C, D as shown, we need to find the work done for each of the four steps. The net work done, work net, and the heat transferred Q net. So we can see that from A to B, the system is undergoing isobaric expansion at 300 kilopascals. From B to C, we can see that isochoric cooling is occurring, and from C to D, we can see that isobaric compression at 100 kilopascals is occurring, and from D to A, isochoric heating is occurring. So to work this problem out, from path A to B, where isobaric expansion is occurring, we can see that work from A to B can be calculated by pressure into the change in volume, which can be represented as 300 kilopascals into 3 minus 1 meter cube, which is equal to 300 into 2, which is 600 kilojoules, which is the work done by the gas. From path B to C, we can see isochoric cooling, where work BC is equal to 0 because delta V is equal to 0. In path C to D, we can see isobaric compression, in which we can see P into delta V. The same formula can be applied, where 100 kilopascals is the pressure applied, and the change in volume can be taken by 1 minus 3 meter cube, which is equal to 200 kilojoules, which is work done on the gas, which is negative. From path D to A, isochoric heating, we can see that the work done is 0 because the change in volume is 0. The net work done here can be done by adding all the work done by each step of the cyclic process. So adding 600 kilojoules and subtracting 200 kilojoules, which is the work done on the gas, we get plus 400 kilojoules, which is the net work. Okay, moving on to numerical number 2, we can see that for a system that undergoes a 3-step process, we need to calculate the unknown energy values by applying the first law of thermodynamics. For process 1 to 2, heat is given as plus 200 kilojoules and work done is given as plus 50 kilojoules. For process 2 to 3, heat is given as minus 100 kilojoules and internal energy is given as minus 120 kilojoules. For process 3 to 1, we can see that the work is minus 80 kilojoules. So we can say this is a triangular process. So the things we need to find here are the change in internal energy, the work done, the heat and change in internal energy for path 3 to 1, and the net heat transferred, the net work done, and the total change in internal energy for the entire cycle. So we need to solve for the unknowns. We'll use two main rules, which is change in internal energy is equal to net heat transferred minus the work for any single step, and we can take that change in internal energy is equal to 0 for the whole cycle, because for a cyclic process the change in internal energy is 0. For the first process from 1 to 2, change in internal energy is equal to Q minus W, which is 200 minus 50, giving us 150 kilojoules. For second process 2 to 3, we can arrange the law to find work. That is minus 100 minus 120, which gives us plus 20 kilojoules. For the third, to find change in internal energy for the last step, we need to use the cycle rule. So since the total change in internal energy is 0, we need to add minus 120 to 150. So our total change in internal energy must be 0. This means the change in internal energy for process 3 to 1 is minus 30 kilojoules. Finally, for process 3 to 1, for the last step, that is minus 30 plus minus 80, which is minus 110 kilojoules, which is the work done. So as a final check, we need to check if Q net is equal to work net. Summing up all the Q values gives us minus 10 joules, so summing all the work values from all the 4 steps also gives us minus 10 joules. Since they match, our solution can be verified as correct. To summarize today's session, for any cyclic process, the system returns to its initial state. So the net change in internal energy for a cyclic process will be 0. This simplifies the the first law, saying the heat transferred net is equal to the work done net. On a PV diagram, the net work done is the area enclosed by the loop. Clockwise cycles produce work. So basically the area inside the loop and the direction of the loop tells you if it is an engine or a refrigerator, which is an application of this cyclic process. Thank you. And these are the various sources used for this session. We have used K.V. Narayan, a textbook of chemical engineering thermodynamics, and Atkins Physical Chemistry, the 11th edition by the Oxford University Press by Atkins and De Paula. Thank you, everyone. And here, so you can refer to various other numericals from this topic in these given sources.